Hello, this is Mrs. Hanson, and this is the Chapter 15, No Calc Practice. Okay, and as always, please do not sit here and watch this whole video, but for the ones that you're still struggling with, scroll to that particular question and see if my little 1 minute or 2 minute synopsis helps you. And for heaven's sakes, just because I said it doesn't mean it makes any more sense to you. So if there's something you're unclear on, please make sure that you talk to your teacher about it. All right, let's get started. So we're going to do number 1 first. It says, which of these buffer systems can absorb the greatest volume of 0.1 molar NaOH without a major change in pH? Okay, so this is basically a buffer capacity thing. We didn't really talk too much about this, but the bottom line is the greater the moles of buffer material, okay, the more NaOH and or HCl that it can consume. So I'm looking for highest molarity here. So I'm going to say A is the best answer just because the molarities are the highest, okay, with 1 molar solutions versus 0.5 versus 0.25 versus 0.1. 1 molar solutions are going to do the job best. And keep in mind that it really doesn't matter, this is a base buffer system because it's NH3 and NH4Cl. It doesn't really matter. Bottom line is any good buffer system should be able to consume NaOH, strong base, and strong acid, okay, whether it's like HCl or whatever strong acid you want, okay? So greater molarity, greater buffer capacity, awesome. We got that. Okay, so that's number 1. Let's take a look at number 2. Okay, so this question, really important stuff. It says, arrange the 4 buffer systems in the table from lowest to highest pH by buffer. So that really has to do with the pKa for each one of these. Okay, so I'm going to roughly estimate based on the exponents. I'm going to take the negative log of each one of these Kas. So 5.6 times 10 to the negative 10th. Well, negative 10 is the exponent, so we're going to go 1 pH unit lower. We're going to say that this guy's pKa is in the range of 9 to 10. All right, so the HF-NaF, negative 4 is the exponent, so that's going to be in the range of, that does not look like a 3. In the range of, that really doesn't look like a 3 either. How about 3 to 4? Oops, I'm trying here. Okay, and then this next one is 10 to the negative 5th, so that's going to be in the range of 4 to 5. And last but not least, to the negative 4th, that one's also going to be in the range of 3 to 4. Okay, so basically 2 and 4 are pretty similar, but HF-NaF is a slightly larger, Ka value, so that's going to be lower. Okay, that's going to be closer to the 3 range. Okay, closer to the 3 range, and this guy is a smaller Ka value, 4.0 times 10 to the negative 4th. So that's not going to be as acidic of a buffer system, so that's going to be more on the 4 side of things. Okay, so now we can put those in order. So, and be really careful. Read the questions carefully. It says from lowest to highest pH by buffer. Okay, so we're going to start with the most acidic one. Okay, so the most acidic one is looking like that HF. So I would say your answer is letter C because HF is going to be, let me see if I can use a different color. HF is going to have the lowest pKa, meaning most acidic, followed by this guy, so 4, followed by choice 3, buffer system 3, and then this guy is going to be in the basic range, okay, choice 1. Okay, so what do you think? All based on the pKa. All right, rolling right along. Let's look at number 3. Okay, so number 3, it says, if a buffer with a pH of 3 is needed for a certain application, which of the components could be used to produce the most effective buffer? So again, one of the big things that I'm sure you remember is whatever pH you desire, so pH 3, you want to start with the pKa that's closest to that. Okay, so looking at our choices, we're definitely going to pick letter B as our choice because, like I said, based on the pKa, this particular one is in the range of 3 to 4, but closer to the 3 side. So letter B is your answer. Okay, good. So just to recap, for whatever buffer system you want to, for whatever pH you desire, you want to pick the buffer system that has the closest pKa to the desired pH. Okay? All right, looking good. Let's go on to number 4. Okay, so this one, number 4, says a buffer is prepared by mixing 50 mils of 0.1 molar NaOH with 100 mils of 0.2 molar ammonium nitrate. Which net ionic reaction best represents what occurs when 25 mils of 0.2 molar NaOH is added to the resulting solution? Whew, so a lot going on there, but you know what? Anytime I read a problem like this that just has so many things mentioned, I'm going to tell you, I would start with the strong whatever, whether it's a strong base or strong acid. Okay, so I'm going to start with that NaOH and say to myself, okay, well, gosh, given the choices here, what would the strong base react with? We got this NH3 component and we got this ammonium nitrate component. Hopefully when you guys think of ammonium nitrate, okay, hopefully you're seeing that the nitrate would be basically a spectator, okay, and the NH4 plus is the active player there. So I'm going to say to myself, we got a strong base here. It's going to react with the acid component of this buffer. Okay, so the acid component would be the NH4 plus. Okay, and I already got rid of the nitrate because we know that's the spectator. So what are we going to make here? This guy acting as the conjugate base, whoops, okay, is going to donate that H. We're going to make water, and we're going to have NH3 left. Okay, so we're pretty close to net ionic. I guess the only other spectator that we would see is I'm going to go ahead and get rid of the Na+, okay, because that's a spectator. So I would say that's the basis of my mice table, meaning the strong base is going to react with the acid part of this buffer system. If there's anything else mentioned in the problem, like NH3, that ends up being one of the products. So that, my friends, would be choice B. NH4 plus OH minus yields NH3 plus H2O. They're all single arrows, but that's definitely appropriate here because this is a mice table, meaning it goes to completion because of adding the strong base. All right, so that looks pretty good. And then number 5. Ooh, I really like number 5. So that means that you probably see a question like that for sure on the test. Okay, so for number 5, it says which set of two solutions, when poured together and thoroughly mixed, would result in a buffer. So some of these you can totally cross off the list very quickly. Like basically strong acid plus strong base is never going to be a buffer, ever. There's no way, shape, or form that I could see that happening. So A is out, just won't be a buffer. Okay, and then D is out too because it has a strong acid, and the only other thing present is HCl and its conjugate base, and we know that that's not the makings of a buffer. Okay, so A and D are out. Now B and C are both contenders. Okay, so and the reason why I would know that is because it has something weak in it. So anytime you see something weak present in the mixture, I suppose there might be some potential for being a buffer. Okay, so now I have to ask myself one question. Does anything react in these mixtures? So when I look at letter B, I see, let's see, HCl and I see NH3. Okay, well, gosh, that is definitely going to react. So I'm going to stick to net ionic. So I got rid of the Cl minus. So the strong acid is going to react with this weak base. Absolutely. Okay, so we're going to make NH4 plus. Folks, that sounds like a mice table. Okay, so I'm going to go ahead and map out my values. Let's see, 50 mils of 0.1 molar HCl. Okay, so we'll do a little mental math rate real quick. Whoops, we'll try. Oh boy, sorry. 0.05, okay, because I converted it to liters, times 0.1. Okay, so hopefully you guys are all right. And let's see, 1, 2, 3 decimals. 1, 2, 3 decimals. Okay, so we're looking at, I'm going to make that line a little thicker again, 0.005 moles of H plus. And then we got the same amount of NH3. So that means 0.005 moles NH3. Doesn't make any mention of NH4 plus. Okay, so my question to you is, what's my limiting reactant? Or I think you guys are to the point where I might say, boy, what point in the titration am I at? Okay, so if you guys think about it, there's no limiting reactant, or you could say they're both limiting reactants. Okay, in other words, if this was a titration, we'd be at the equivalence point. Okay, we've added enough strong acid to basically neutralize the OH minus. So these two are both going to go down, okay, to 0, 0, and then all the NH3 got converted to conjugate acid. Okay, so classic, what's going on at the equivalence point? Okay, so mice table, and if you wanted to learn the pH of this is a mice ice. So meaning it's a mice table, followed by the fact that this NH4 plus, the only thing present, would then further hydrolyze. So this would not be a buffer solution. And in fact, it would be a slightly acidic solution, okay, due to the conjugate acid hydrolyzing. And hopefully, if you guys were asked, you could definitely work through and figure out what that pH is. Okay, you could do the hydrolysis of this guy, make sure and get the appropriate Ka, make sure and convert this to the molarity, and you could get the pH at this point. Okay, but bottom line is B is not the answer because it's not a buffer. Okay, so let's look at choice C. So exact same mixture, HCl plus NH3. So I'm basically going to use the same reaction if that's okay. Let's see. It looks like my moles of H plus is exactly the same, 0.005. But the big difference is this guy. Okay, we have twice as much NH3. So instead of 0.005, we're looking at 0.010 moles. And this guy's still 0. So this time we're at a different point in the titration. So the H plus is a limiting reactant. Okay, so we've added enough H plus to neutralize half of the NH3 and convert the other half to NH4 plus. So this guy goes down to 0. Okay, this guy, half of it reacted, so the other half remains, and this guy has gone up to 0.005. So then I ask you the same question. If this was a titration, what point in the titration would you be at? And I hope you're thinking, you're yelling at the top of your lungs, you'd be at the half equivalence point. Meaning the definition of the half equivalence point is you've added enough strong whatever to neutralize half the weak whatever, leaving the other half behind. Okay, these two numbers right here match. Okay, so you're at the half equivalence point. So hopefully you automatically know that the pH would equal the pKa at this point. And furthermore, it's definitely a buffer because you have weak base and you have conjugate acid both present. They don't have to be 1-to-1 like that, okay? But you have to have numbers in both this spot and this spot, and it's a buffer, okay? So just remember, we've talked about some of these examples before, and you can make a buffer, okay? But you got to have the right amounts, okay? And the take-home message is the strong whatever has to be the limiting reactant. It has to be gone, okay? If you have any strong whatever left, okay, then it's definitely not going to be a buffer, okay? And furthermore, you can't be at the equivalence point, okay, because that won't be a buffer either because the NH4 plus will be the only thing there and it'll hydrolyze. So, I think that was a really long answer, but I'm telling you, that is an important question, okay? And if you feel like you need more practice, we did some of these on page 33, 34 in the binder. Key is posted on Schoology. And actually, on the next page, it's optional practice, but page 35, 36, I think there's some other practice just like that, okay? So, if you need to, go ahead and make sure you practice these, okay? All right, let's see. Boy, let me erase that. Okay, before I totally erase it, though, I'm going to say one more thing. When it comes to these types of problems, you should have it in your head that really there's only ever 3 options. So when you get to the bottom of the mice table, your first option is it a buffer? Is it a buffer? Okay, like this one, because you had an amount here and amount here, so you could use Henderson-Hasselbalch to solve. The other option was letter B, are you at the equivalence point? Are you at the equivalence point? So the way you recognize that is this is 0 and this is 0, and the only thing you have present is conjugate whatever, which is going to hydrolyze. And really the only other option is, do you have leftover, what do we want to say, strong acid or a strong base? If you do, the strong acid or the strong base, whichever one you have left over, is going to rule the pH. Okay, so you're going to determine the pH by looking at the excess strong acid or strong base. So those are your 3 big options. And gosh, if you can apply that every single time, that's money right there. Okay, sorry, long answer for that one. I hope that helped. All right, moving on. How about number 6? Okay, so the above diagram represents a titration of a strong base with a strong acid. How would the diagram differ if 0.1 molar NH3, a weak base, was titrated with the same exact HCl? Okay, well, I'm a visual person, so I'm going to draw that in. So visually, that might be how the weak base titration looks different. So some notable differences. One, the strong base starts off much more basic. The weak base does not start off as basic, okay, because the weak base doesn't dissociate as much. Notice that the weak base has this distinct buffer region, okay, whereas The strong base, it just sort of, it's more of a gradual, okay, increase. It just looks different. Okay, it doesn't have that buffer region. Okay, and that's basically it. Okay, but one thing that you notice is exactly the same for these guys is the stoichiometry is kind of the same for both of them. They're being titrated with the same strong acid, and you started off with the same molarities and the same amounts. So their equivalence point will be at the exact same place. So what I want you to remember is that whether it's a strong acid or a weak acid, totally doesn't matter. If they're the same molarity, same volume, it will require the same amount of base to neutralize. Okay, just NaOH, strong acids or strong bases, they don't discriminate. Okay, they will neutralize any H plus, whether it's strong or weak or someplace in between. Okay, so therefore, it said, boy, I can't even read the question anymore. Okay, it said, how would the diagram differ? So let's see. I think we answered most of these questions. So it looks like C is our best answer. Okay, and the reason for that is, yes, the initial pH would be lower. The length of the vertical range is shorter. So what that means is, like, for the strong, like, that's your vertical range. Okay, for the weak, for the weak strong, okay, for the NH3, notice the vertical region is, let me see if I can use a different color there. There we go. The vertical range is more like, okay, like here to here. Okay, this line right here. Okay, so yes, just because that weak base starts off at a lower pH, it just does not allow as much of a vertical range. Okay, do you guys see how that works? Volume at the equivalence point is the same. Okay, and that's kind of my major point here. And the equivalence point pH, okay, so my picture's getting kind of muddled. Let me clean it up. So if this was, of course, strong, NaOH with HCl strong, the pH is at 7. Okay, if I titrated the weak base, it would look something like this. Equivalence point would be right there, and it would definitely be acidic. Okay, and hopefully you know why. Keep in mind, at the equivalence point, the only thing you'd have present is the conjugate acid, which would hydrolyze. Okay, and that's what would make the pH acidic at that equivalence point. Okay, all right, good question. I like that one. Let's move on to number 7. Whoops, I meant to circle that. I did. Woo, let's see, number 7. Okay, it says, in the titration of nitrous acid with NaOH, which indicator would most accurately show when the equivalence point is? Okay, so like I said, I'm a visual learner, so I'm going to go ahead and sketch kind of what that titration curve might look like. Okay, so here's my good old equivalence point. Okay, and that's I want the indicator to change colors right there. Okay, so just keep in mind the whole story with nitrous acid. Okay, is that if I go ahead and titrate it, that's an O. Okay, like this would be the basis of my mice table. It's going to make water, and it's going to make, oops, I hope I can fit this in. There we go. And it's going to, you'll be left with the conjugate base. So keep in mind, just like we talked about a minute ago, at the equivalence point, you will have added enough base to neutralize the HNO2. So both these are going to go down to 0. And then all the HNO2 will have gotten converted to NO2 minus. Okay, and NO2 minus, whoops, that's a plus. NO2 minus at the equivalence point, okay, it will undergo hydrolysis, producing that OH minus. Okay, so that, my friends, is why this pH right here is going to be like 7 would be here. So this is going to be basic. So long story short is I look at these indicators, I need to pick one where the pKa is basic. Okay, so just to remember, the way that indicators work is that you want the pKa of the indicator, okay, to be as close as possible to the pH at the equivalence point for what you're titrating. Okay, so there you go. So this guy right here is basic. Okay, so that means I need the pKa of my indicator to be basic. So this guy is definitely out. This guy is definitely out. Those two options are both pretty good. I went with phenolphthalein because 7.3, I mean, that's pretty neutral. Okay, so 9.5 seemed like a better bet, but I could see those both being sort of decent choices. Okay, so that means that phenolphthalein, basically, it's going to go, it's going to be at its pKa, so it's going to be a perfect mixture of colorless and red at 9.5. So that's probably going to happen, I don't know, depending, it might happen like right there. Okay, which is close enough, as close as we can get to this basic pH. Okay, so that's kind of what we're looking at there. What about number 8? So it says, what color would the solution be at a volume? Ooh, this one's a little tricky. Okay, let me see if I can clean this up a little bit. Okay, so it said, what color would the solution be at a volume equal to half of the equivalence point of the titration of acetic acid? Okay, so let's see. We got a different titration. Okay, so it looks something like this. Looks pretty much the same as the nitrous acid. Okay, but this time it's acetic acid. Okay, so let's see. This is my equivalence point. So it says, what would be the color of the solution at a volume equal to half the volume of the equivalence point? So if this is my equivalence point, I'm really talking about this volume. I'm really talking about the half equivalence point. Okay, so basically, what color would the solution be right here? Not a normal question, because you normally don't want the indicator to change colors right here. You want the indicator to change colors here. So this question's, it's kind of weird. Okay, I kind of like it. But one thing you do know is that, okay, this is a half equivalence point. So what would the pH be at the half equivalence point? Well, for this titration, we got acetic acid. Its Ka is 1.8 times 10 to the negative fifth. You guys have done that one enough to know that the exponent is negative fifth, so you go 1 pH unit below. It's going to be between 4 and 5, but I think you guys have done this one enough to know that that's going to be 4.74, right? From the Buffer Lab practical and all that. So that's where you're at. You're at a pH of 4.74. So what color is methyl red going to be? Well, let's go up and look at methyl red. Okay, methyl red is red in its acid form, yellow in its base form, and its pK is 5. So that's when it changes color. So at a pH of 5, methyl red is going to be an equal mixture of the red and the yellow form. So it's going to be orange. Okay, and you remember that color change, it doesn't happen like boom, okay, right at 5 only. The way that we said it is it's going to happen 1 pH unit below and 1 pH unit above its pKa. So basically, its color changing range, I suppose, is going to be 4 to 6, right? 1 pH above, 1 pH below. So bottom line, if, 6, let's see, if 6 is like right here and 5 might be right here, okay, that right there is, during that range from that pH, from pH 5 to pH, actually, I wanted to say pH 4, okay, all the way up to pH 6, okay, it's going to be orange. So in this range right here, so in this point that we're talking about, it's in the orange range, okay? And then you guys might conject that, okay, so if it's orange between a pH of 4 and 6, what color is it going to be like up here, okay? Well, this is past the pKa. This is more basic than the pKa. So up here, any pH past like 6-ish, it's going to be yellow. And then, of course, if you're more acidic than the pKa, so if your pH is below 5, okay, or below 4, because that's where the color change is taking place, then it's going to be red. Okay, so that's sort of like how the color change would work here. It would be red, okay, and then, the color change would take place, and then yellow, okay. So this would not be a good indicator for this titration because, it certainly did not indicate the equivalence point, okay? So hopefully that makes sense. It was kind of a unique question, okay? Not a bad question, but just a little different. Okay, so again, I keep telling you, just because I said it doesn't mean it makes more sense. So talk to your teacher if you just want to hear it again or hear it in a different way. Okay, whatever you need. All right, rolling right along. We made it to the backside. Okay, number 9. Let's see. And if you guys excuse me, my light turned off in my classroom, so I'm going to turn it on. Whew, okay, I'm back. So number 9, this one, another indicator question. It says if bromothymol blue turned green at the equivalence point, of a titration, what must be true? So I'm going to go back for a second. Bromothymol blue. Okay, so its pKa is 7.3. Okay, and green, of course, is a perfect mix of yellow and blue. So basically, at a pH of 7.3 at its pKa, and then 1 pH unit below 6.3, 1 pH unit above 8.3. That's basically when it's going to be green. Okay, so what would you be titrating if basically your equivalence point is pretty darn close to neutral, is what I'm seeing here. So when I go back to my choices, that's why I thought D was the best answer, because the titration involves a strong acid and strong base. The one thing I know about that titration, okay, is that no matter what, the pH is going to be pretty much right at 7 for the equivalence point. Okay, now you may have thought about maybe choosing choice A, because titration involving a weak acid and a weak base, that could have a titration close to 7, but it really depends on what the weak acid is and what the weak base is. You might remember that in the lab, we titrated this guy. Okay, we titrated NH3 with acetic acid, so it was like weak with weak. And if you remember, basically the H got donated and you made ammonium acetate. So this is what was present at the equivalence point. Okay, so you added enough acetic acid to react with all the NH3, so those guys both went down to 0, so everything got converted to this. And you might remember that the Ka for ammonium and the Kb for acetate, these two guys are equal. So gosh, this guy would also have a pH of 7 at the equivalence point. But that's pretty unique to this salt because of the Ka and the Kb. So that's why A, I mean, it could be true, but as soon as the language says must be true, I'm going with D as a safer answer. Okay, so that was an interesting one. Let's see, how about number 10? It says separate samples of equal volumes of 0.1 molar NaOH are titrated with two different acids. Okay, 0.1 molar HCl and 0.1 molar H2SO4. Which statement best describes the volume of acid needed to reach the equivalence point? Okay, well, make sure you guys are sort of visualizing this. Then the burette is the acid, okay, because it says the NaOH was titrated with the two different acids. So your NaOH is down here. Okay, so if you have this 0.1 molar and an equal volume, you sort of have this constant moles of NaOH. Okay, but the acids are different. Okay, and what's different about them is you have HCl with one H and you have H2SO4 with two H's. And like we talked about before, when it comes to strong reacting with strong, nobody discriminates. So basically the OH minus is going to keep reacting until all the acidic hydrogens are gone. So bottom line is, since this one has two H's per H2SO4, you're going to need half as much volume of this. Or in other words, you're going to need double the amount of HCl. Okay? So that's why basically D is the correct answer. Okay, because HCl only has one H, you would need 2 times more in order to neutralize that same amount of base. Okay, so a little stoichiometry piece there. Hopefully that makes sense. Okay, so that was number 10. All right, so next one. Finally, we get into a little math. There's not been too much math on this particular no calc practice. We're going to look at 11. Okay, a student uses acetic acid, okay, to titrate a solution of potassium hydroxide to determine the concentration of the potassium hydroxide. Okay, so I'm going to use HA to represent the acetic acid, KOH for the potassium hydroxide. You're going to make water, and of course the salt. So it's a really simple acid-base neutralization reaction. Okay, if 30 mils of 0.25 molar acetic acid is needed to neutralize 15 mils of potassium hydroxide, what is the molarity? Folks, this is like straight up like last year chemistry stoichiometry. Okay, so I'm going to go ahead and take my volume of acetic acid. I converted it to liters. Okay, and I'm going to multiply that by that molarity. Okay, and right there, that would be my moles of acetic acid. Okay, and then for every 1 mole of acetic acid, you're going to have 1 mole of KOH. Okay, so they're in a 1-to-1. Guys, this is a pretty important step, because if I gave you H2SO4 or something, that wouldn't be a 1-to-1. That would change your answer. So make sure you guys pay attention to that. All right, so I'm going to multiply those. Okay, so basically 25 times 3. Okay, so that's 0.0075. Okay, and that's moles of KOH. Okay, now if you didn't like that mental math right there, okay, this one's a pretty easy one to do. Okay, just sort of like straight up, what do you call it, normal multiplication. Okay, like 0.25 times 0.03, so 15, 6, 7, right? And then 1, 2, 3, 4 decimals, 1, 2, 3, 4 decimals. Okay, so I think you guys can do that, right? Okay, and then we want the molarity of the KOH. Okay, so I have the moles. I'm going to divide by the original volume because I want to determine the original molarity. Okay, so just realize this is not a time where those volumes are additive. Okay, this is a time where you're trying to figure out the unknown molarity of the potassium hydroxide. Okay, so I'm going to convert that to liters. How many times is 15 going to 75? Okay, and that goes in 5 times. Now, in terms of the decimal, I always think when I divide, I just really like using scientific notation. So 7.5, 1, 2, 3, to the negative 3 divided by 1.5 times 10 to the 1, 2. Okay, well, how many times is 1.5 going to 7.5? Well, let's see. 1.5 times 2 is 3. Okay, then if you double that, okay, that's 6. So that's 4 times. One more time. Hopefully you guys see that that is 5. Okay, but in terms of the exponent, it's minus 3 minus a minus 2. So those become add, and it simplifies to a minus 1. So 5 times 10 to the minus 1. So that means you just move the decimal place over 1 spot. So 0.5 would be your answer. Okay, so a little mental math. And folks, I would say this number 11, like that's as hard as it gets. Okay, so if you can do that kind of math, you're going to be fine. All right, so just keep practicing it. If you want me to walk you through some examples with the scientific notation, I love it. I would love to help you with it. Okay, so that was number 11. Hopefully that helped. Oh, so what's the final answer? I think is D as in dog. Okay, all right, moving right along. So number 12. Ooh, number 12. One of my favorite questions. I would put some stars by that. Okay, so number 12, you got solution A. It's just a weak acid solution. If you don't mind, I'm just going to use HA. Okay, but we'll say that's acetic acid. And then solution B is also acetic acid, but it's a buffered solution. Okay, because it has the sodium acetate as well. But look, the reactions look exactly the same. So the difference is for A, you're basically starting off with just some quantity of acetic acid, and it's going to dissociate, okay? But for B, you're starting off with some quantity of HA, and you have an equal quantity of A minus, okay? So it's the presence of a common ion, aka a buffer solution, okay? So the bottom line is there's 2 major effects to that, okay? If this is high, okay, that basically causes this reaction. So if this one goes forward this much, okay, the presence of that common ion is going to cause this guy to go forward this much. It's not going to go as much in the forward direction. So that's definitely going to affect the percent ionization. That's the H plus over the original HA. Okay, so for solution A, this number is going to be a lot bigger. Okay, so the percent ionization for this guy is going to be higher. And because of that, you're making more H plus. So the pH is going to be lower, or meaning more acidic. Okay, so that's why choice A is the best answer. It says the acetic acid undergoes a greater percent dissociation in solution A than it does in solution B, okay? Because B is buffered and A is not. Okay, and while we're talking about that, one of the other things that's different between unbuffered, whoops, I didn't mean to do that, and buffered has to do with diluting. Okay, so I just want you guys to remember this. If you dilute a buffer system like solution B, no effect. No effect on buffers. Okay, and you guys know, that's true because of Henderson-Hasselbalch. It's going to affect the molarities of the 2 active components, the A minus and the HA, the exact same way. So Henderson-Hasselbalch, you get the same pH, okay, meaning like nothing's going to change, okay? Now, if you dilute solution A, yes, actually it is going to change, okay, because when you dilute a normal weak acid, okay, that means you're going to dilute this guy. Whoops, I did not mean to do that. You're going to dilute this guy, and this guy. Okay, when you add water, you're going to dilute all the active species. So it's going to shift in the forward direction even more in order to compensate. Okay, so the percent ionization would become even higher, okay, if you diluted a normal acid solution. No effect, okay, if you dilute a buffer system. Okay, so that's kind of your little bonus on that question. All right, I hope that helped. Whoops, I didn't mean to scribble that out. Okay, how about number 13? All right, 13, really good question. Okay, it says consider 100 milliliters of 0.1 molar aqueous solutions of each of the following acids. So you got HCN, HF, HCl, and acetic acid. Each acid is titrated with NaOH. Once the equivalence points are reached for each solution, rank the pH values from highest to lowest. So I ask you, is this really like an acid thing, or is this actually a conjugate base thing? So if you think about it, like if I titrated the strong acid, the HCl with NaOH, it would probably look something like that. Okay, now the next strongest acid would be HF, and it would kind of look like this. Okay, and if I did the next strongest acid, that would be the acetic acid. And I'm just basing this off the Ka values. So it looks something like this. And then last but not least, the weakest acid on the list is the HCN. So it looks something like this. It's kind of pretty, right? So what I hope that you guys can see is that that equivalence point, it was here. It just keeps moving up. Okay. So just keep in mind, the weaker the acid, meaning the lower the Ka, okay, the stronger the conjugate base. In other words, the greater the Kb. Okay? So, long story short, the weakest acid is going to produce the strongest conjugate base, which will have the greatest pH, the most basic pH. So that would be HCN. Okay, so your best answer there is letter B, because HCN was the weakest acid, so it's going to produce the strongest, most basic conjugate base. And then this guy, and of course HCl is the strongest acid, so it has the worst conjugate base, Cl minus, which is actually a neutral ion. It's such a bad conjugate base, it doesn't hydrolyze at all. That guy's neutral. Okay, so hopefully that helps. Really, really, really great question. All right, folks, we are on the home stretch. Let's take a look at number 14. Okay, I love this question, so you guys can put some stars by that. It says you're asked to make 1 liter of a solution buffered at pH 9. Okay, you're given 1 molar HCN and 1 molar NaCN, so weak acid in its conjugate base. Which statement is true? So I hope the first thing that you thought of was like, oh, this sounds like Henderson-Hasselbalch. Okay, so pH equals pKa, okay, plus log of the base, which is the NaCN, over the acid, which is HCN. So I would say this problem all boils down to this pKa. So the value is 6.2 times 10 to the negative 10th. So can you guys estimate what the negative log of that would be? So negative 10 is the exponent, so go 1 pH unit below. It would be between 9 and 10. Okay, so I'm just going to make up a number. I'm going to say it's 9.2. Who knows what it actually is? It doesn't matter. Okay, so now the big question is, if this is your pKa, okay, then that would be an equal ratio of the base to the acid. So how do you get the pH down to 9? Just like in the buffer lab practical, you're going to have to manipulate this ratio. So if you want the pH to go from 9.2 down to 9.0, guess what? You're going to need more acid, less conjugate base. So that's why the best answer there is letter C. The volume of the 1 molar HCN acid component must be greater than the volume of the 1 molar conjugate. Okay? So really easy question. Definitely something you can do without a calculator. All right, 15. It says you're asked to make a buffered solution with a pH as close to 7 as possible by mixing equal volumes of 1 molar solutions. So I think we talked about this earlier, that whatever pH you desire, you want the pKa of the buffer system to be as close to that as possible. Okay, to be as close to that as possible. So pH 7, okay, so let's look at these exponents. That one's a minus 4. So this guy would produce a buffer in the range of like 3 to 4. Minus 10, so this guy would produce a buffer, that would be a basic buffer in the range of 9 to 10. Minus 8, that would produce a buffer in the range of 7 to 8. Okay, and -5, its pKa is going to be in the range of 4 to 5. Okay, so bottom line, if pH 7 is what you desire, then I would go with solution C, a buffer made from this guy and this guy. So this would be the acid component. This would be the base component. Okay, that would get you as close to 7 as possible. So then you'd kind of do what you did up here to kind of tweak that ratio to get it to 7. Okay, all right, love that question. Finally, 2 more. So let's look at 16. Again, Henderson-Hasselbalch says a certain buffer solution has a pH 4.6. The weak acid used to make the solution, HA, is a pKa of 3.2. Okay, and then you're going to have your base over your acid ratio. Okay, so basically what has to be true, this is where you're at for pKa, this is where you want to be at. Okay, so you have to make it more basic. Okay, so the best choice I would say is going to be letter C, meaning the acid component is going to have to be less than the base component. So that's what that's saying, because the pH that you desire is greater than the pKa. Okay, so bottom line, if you want a more basic solution than the pKa, then you got to have more base or less acid. All right, so that was actually kind of an easy one. And last but not least, 17, it says a 25 ml sample of 0.1 molar acetic acid is titrated with 0.1 molar NaOH. What is the pH after 25 mils of NaOH has been added? So I think what you got to think about is, gosh, what point in the titration am I at? So 25 mils of 0.1 molar, and I'm adding 25 mils of base, also 0.1 molar. Okay, so it looks like equal molarities and equal volumes. Folks, we are at the equivalence point. Okay, so if you think about this acetic acid, again, I'm being lazy, with the OH minus, if you think about your mice table, you're going to make water, and you're going to have A minus. So at the equivalence point, you've added enough base to react with the A minus. These guys both go down to 0. All that HA will be converted to A minus. Okay, so what's A minus going to do to the pH? Okay, A minus being a conjugate base is going to hydrolyze. Okay, so it's going to react with water to make HA plus OH minus, which is going to make a basic solution. Okay, so, that's what's going on behind the scenes. So definitely A is out, B is out. So you're like, C and D, they're both basic. But the bottom line is it's a conjugate base. Okay, so I'm going to say 8.87 seems much more reasonable, just because 12.77 seems too basic. Okay, all right, well, good luck. I hope something in this video was helpful. If you still got questions, please talk to your teachers. And good luck with your preparation. Thank you for listening. Have a great day.